In this video, we will develop the vector equation for a line in 3 space. To develop this vector equation, we will use the coordinate-free idea of vector subtraction. You might think, why do we need to do this? Because we have this very familiar y equals mx plus b, and that works in the plane, but it does not work in 3-dimensional space. On the other hand, the equation that we develop in 3 space will reduce to y equals mx plus b in the plane. So we start here with our coordinate-free idea of vector subtraction that we developed before. In order to write the result of vector subtraction, a minus b, in this form, this triangular form, we wrote b plus a minus b is equal to a. There was another way to handle vector subtraction, but it didn't give us this triangle, and we like this triangle. So this is the form we're using. Now if we write this as b plus 1/2 a minus b, then we end up with the vector m. M is for midpoint, because the vector m is pointing to the midpoint between the tips of b and a. To develop the line, though, we're going to want to go to coordinates, so we're going to map all this terminology into something that's typically used. So b is going to be called r0. A is going to be called r1, and this difference, a minus b, will also have a new name, and that name is v. This vector m, which right now is pointing to the midpoint between the tips of b and a, gets the name r, and it is from this r that we develop, or based on this r, that we develop the vector equation for the line. One thing that has to be noted here is the vector v. Okay, r0, r, and r1 are all position vectors because they are tied to the origin of the coordinate system. Their initial points are at the origin of the coordinate system. So these are position vectors, but notice that v is not. V is a vector in general, and as you know, vectors can be moved around the plane as long as they keep their same length and their same direction. So instead of writing v down here, right down here, coming off the origin, like r0, r, and r1 are, we treat it instead as a position vector, or as a general vector, and we place it between P0 and P1 for convenience. It gives us the visual effect that's similar to this, and we can use the idea. The idea is of vector subtraction, and m sort of moving around between the tips of A and B, and that's what we're going to do with r. That is why v is sitting up there, but v is not the vector equation for the line. It's just a vector that's conveniently placed there. This is an important point, and sometimes students miss this. On the previous page, I could have written that equation for r as r0 plus 1/2 v, because it pointed to the midpoint between P0 and P1, just like the m for the coordinate-free case pointed to the midpoint between the tips of the vectors a and b. But there's nothing special about the 1/2. So I'm going to change that 1/2 to a 1/4, and the result is that the vector r will point here, 1/4 of the way from P0 to P1. If I change it to 3/4, obviously it's going to point here. Now we're still not restricted to these fractions. We could write, for example, minus 1/4. In that case, r would be pointing way over here. And what is the point? Where is it going? It is pointing to a point along a line through P0 and P1. The vector v is sitting on that line, okay, but it is not the line, and that line will extend. We can go the other direction also by using, for example, minus 5/4. And right now, we are ready to write the equation for the line. We write it as a parametric equation. R, and the parameter is t, a scalar, equals r naught, the position vector to the point p naught, plus t times v, which is that vector between p naught and p1, sitting there between p naught and p1. This is the vector equation for the line. R is a position vector, and as t changes, it points to all along this line. So here we can write it a little bit more if we use some coordinates for the 2 points. So here are coordinates for the 2 points. We construct r naught and r1, and from that we construct the vector v. Notice we had to construct r naught and r1 in order to write v. However, numerically, v is going to look like this. x1 minus x naught, y direction, plus y1 minus y naught in the j direction, plus z1 minus z naught in the k direction. So numerically, we're just taking the coordinates off of here, and we're forming this vector v. But theoretically, we cannot do that because scalars can't just arbitrarily make up a vector. But this is how it looks. Then we have the equation for the line here. Oops. R of t, r is a function of t, parameter t equals r naught plus tv. Again, we will now need r naught as a vector, v is a vector, t is scalar multiplying v. And r naught ends up being right here at this point, and this point has coordinates x, y, z, which we're reading off of r, and these coordinates depend on the value of t. Here's an example with some numbers. Here are the 2 points, coordinates 1, 10, and 4, and for P1, coordinates 4, 5, and 6. Now we have 2 position vectors. We subtract those position vectors and we get a vector for V. 3 in the I direction, minus 5 in J, and plus 2 in K. The equation for the line is R of t equals R naught plus TV. Again, V by itself is not the equation for the line. So we R naught, so we have a, I'm going to erase this for a second. So for the x coordinate, we take the x coordinate of R naught, and t is multiplying the x coordinate of V, and that's the x coordinate. And similarly for the y's. You can see at this point the R1 is not even used. It was only used to construct the V. After that, it doesn't appear in this equation. Now let's look at some special cases, which if this didn't work out, we'd be in trouble. So it's R0 plus T times V, but what is V? It's R1 minus R naught. So if T is 0, R is pointing to R naught, right along to that first vector that we had, pointing to P0. And if T is 1, then of course the R naughts would subtract off, and R would be pointing to R1, which is pointing to P1. So if R is confined to the intervals 0 to 1, then T is pointing to the line segment between P0 and P1. If T is not restricted, then R points to the line meaning the infinite line that goes through those points. We can also rearrange this equation to give it a little bit of physical significance. If we write v as a unit vector here, then what that unit vector means is, it's a unit vector pointing in the direction of v. And you can think of this form as the path of an object. So here is a starting point. This is the speed. And this is the direction. And here's just another example. In this case, we started with P naught, this is 2, 3, whoa, that shouldn't be there. Well, start over again here for a second, but we will eliminate this. We'll keep eliminating it until it's not going to go away. Okay, so what's P naught? It was 12 minus 6 and 4. And we can read off the coordinates for P1 here from R1, 3, 2, and 3. Now from those we construct the V by subtraction. And this is the equation for the line in the usual form. If we want to construct that unit vector idea, we have to take the magnitude of V. Remember what the magnitude of V is. Okay, it's going to be the square root of V dot V. And so we have minus 10 squared plus 9 squared minus 2 squared, which gives us the square root of 185. And using the second form, we then leave R naught by itself, because that's the starting point. This would be the speed, and this is the unit vector in the direction of V. Now we'll write this in a different form, actually in a scalar form, but to do that, first we give a new name to the components of V. We call them the direction numbers. Right? And they're usually listed as lowercase ABC. So in that case, we can write R of t as x naught plus AT, and then for the I direction, for the J direction, Y naught plus BT, and for the K direction, Z naught plus CT. So these are the direction numbers, and now we're going to take this expression and we're going to develop what's called the symmetric equation. So for the symmetric equation, let's look at R in two forms. Here it is where we use those direction numbers. We just did that on the previous slide. But we know that R of t has coordinates x, y, and z. That's the value at the tip. That's the value at the point along the line to which R is pointing. And now let's equate the x components. So x equals x naught plus AT. Doesn't seem like much, but solve for t. T is x minus x naught over a. And we can do the same thing for the y components and for the z components. Now since all three of these, I'll highlight them here in some color. This, and this expression are all equal to t. They're all equal to each other. And by writing them all equal to each other, that is called a symmetric equation for the line. Sometimes this is used to compute various things, but what it's interestingly very useful for is to show that this equation in 3 space reduces in the plane will reduce to the y equals mx plus b. So here we are starting with the equation in the symmetric equation in general. But if z equals z naught, then the last term is going to drop out. We will not worry right now about c, so this is gone, and we just end up with x minus x naught over a equals y minus y naught over b. This is the equation for a line in a plane perpendicular to the xy coordinate axis, but offset by z naught. And we had the xy coordinate planes in the first lecture. And the equation for that was z equal to 0. So this more general z equal to z naught is also a plane, and it is parallel to the coordinate axis, the coordinate plane, the coordinate xy plane, but it could be, if z naught is 2, then it's running through z equals 2. So this is a planar equation. It can be rearranged to solve for y, and we end up with the form y equals mx plus b. You can see the term b over a is just a constant that will take the place of slope, and this other term here, y naught minus b over x naught, is also a constant, and it takes the place of b. So that's very reassuring that whatever we did in 3-space reduces to what we know and believe for 2-space. Okay, so that's the vector equation for the plane. Main point to remember is that v is not the vector equation. Here it is. R of t, there's parameter in here, equals r naught plus t times v, where r is a vector, r naught is a vector, and t is also a vector. I mean, v is a vector and t is a scalar, the parameter for this equation.